Wait 1 second.
Yes.
Okay, we are now live. You can go ahead. Thank you.
Okay. Thank you. So it's a pleasure to introduce today's pizza seminar speaker, Santiago Gonzalez-Gaitan, who is visiting us for a month. I actually don't know until when you are staying.
26.
Okay, so you're at the beginning of your
Yeah,
stay
yeah.
here. So that's good. So if you want to interact with him, you have plenty of opportunities still. So his background is that he got his PhD in 2011 from the University of Toronto. And then he went to Chile, to the University of Chile, for a 5-year postdoctoral position. And since then, since 2017, he's been appointed as a researcher and also a professor at the University of Lisbon, which is still his current home institute. He's visiting us from the University of Lisbon. His area of research is supernovae, their host galaxies, and a little bit of cosmology. So please, Santiago, go ahead.
Well, thank you very much for being here and for the opportunity for me to give this talk. It's a great pleasure to come to Barcelona and work with the supernova people here. So I've been working in the last years in dust extinction, basically towards supernovae and their host galaxies. And I'm going to show you that this is a very, very important topic, obviously even beyond supernovae, but also galaxies and cosmology in this case. Oh, wait, it's not changing. Okay. So supernovae, are the bright explosions of stars at the end of their lives. They can outshine their entire galaxy. Here, the supernova, you can see as it evolves. This is the brightness as a function of time. And it's actually very convenient, this one, because it's in a very big dust plane. This is in Centaurus. And you can see also the spectral evolution. It becomes colder as time evolves. Supernovae can last weeks, months. And so they're very bright and they expel a lot of material very fast. And it goes into the interstellar medium. And many hundreds of years later, you can see supernova remnants, right? And supernovae, so the typical observations we have of them are light curves, so the brightness as a function of time in different filters here. But we can also have the spectral evolution, and where you can recognize different lines as the supernova evolves. You can also have polarimetry, and I will briefly mention that. These are the typical things that we observe, but supernovae come in different types. So I cannot see actually this. Maybe I can move this. Yeah, okay, good. They come in different types. So an observer will tell you, okay, if they have hydrogen, then we call them type 2. If they don't have hydrogen, we call them type 1. And you can subdivide this type 1s. Also, if you see silicon, then we call them type 1As. They have helium, type 1Bs. If they don't have either helium or silicon, we call them 1Cs. This is like the most traditional supernova subtypes, but there are many more nowadays, and I'm not going to talk about them. From a theoretical point of view, then this case is simpler. 1Bs, 1Cs, and type 2s, they are core collapse. So basically, this is the end stage of massive stellar evolution. We reach an iron core. We cannot produce more energy through fusion, and it collapses, and we have a core collapse supernova explosion. In the case of type 1As, this is a low mass star, so a white dwarf in a binary system, and this white dwarf accretes mass from this companion, reaching the conditions for a supernova runaway, thermonuclear runaway explosion. And in this talk, I'm just going to talk about type 1A supernova. And so, although we know that this is a white dwarf in the binary system, we don't really know what is the companion and what is the explosion mechanism. There are two main traditional scenarios, and there are more, but I'm going to focus on these two. The single degenerate scenario, so basically you only have a degenerate star, which is the white dwarf, and the companion is a non-degenerate, so a main sequence or a red giant or something like that. Whereas in the double degenerate scenario, you have two white dwarfs that slowly coalesce together, they fuse, and you have the thermonuclear runaway. So type 1A supernovae, they're very popular because they're used as standard candles for cosmology, so to measure distances. And to give you an idea of this, this is a sketch of the Hubble diagram where you have the velocity in the y-axis, the distance, and so you observe that objects are moving away from us, and the further they are, the faster they move, right? This is the the expansion of the universe that was already more than 100 years ago. But for this to really work, we need standard candles. What is a standard candle? Is something we know the intrinsic luminosity, and then when we see it weaker, when we see it fainter, it means it's further away, and it's not intrinsically fainter because we know its actual luminosity. That's a standard candle. And type 1a supernovae are supposedly standard candles, and I'm really saying supposedly because there's a lot of controversy. And we to first say they're standardizable candles. What does that mean? They actually don't have all the same intrinsic luminosity, but they do have things we can correct it for. For example, here on the upper right, you see a bunch of different light curves of supernovae, and clearly they have different peak maximum, peak brightness. So they don't have all the same brightness. But what is interesting is that the ones that are brighter, they evolve more slowly, right? And the ones that are fainter, they evolve faster. And this evolution, it's called the light curve width of the type 1a supernovae. And we can correct for that. So the brightness depends on that light curve width, sometimes also called stretch, in a linear way. And so if we correct for that, then look at this. You can see that they're roughly now have the same peak brightness. This is for more than 200 supernovae. There's still a bit of scatter, but you can correct and use them as standard candles with one correction. But there's a second correction, which is the color correction. And we know that type 1a supernovae that are brighter, each point here is a supernova, they're also bluer, whereas the ones that are fainter, they're redder. So we can also correct for that effect. And so basically doing two corrections, this is the stretch or light curve width correction, with the brightness, so it has a linear relation for this alpha that we can correct for, and the color is also linear, kind of linear relation with brightness for this beta parameter, and then we can correct and obtain distances with type 1a supernovae. And this has been very successful in the past and has led to the discovery of the accelerating universe. Here is again a Hubble diagram. Here you have the apparent brightness, the redshift, right? And each point is a supernova at different redshift, and the lines are different models. This is back in 1998. And you can see that the only matter model, which are the ones in the lower part, they're basically ruled out from the data. And so the idea is there is something that is making the supernovae that are further away fainter. So maybe the universe has expanded more. Maybe we're going through an accelerated phase of the expansion, driven by some dark energy component, right? So basically, we see here's the dark energy. This is the matter content of the universe, and it's consistent with none being zero. So there is the acceleration of the universe, and today the dark energy makes up more than 70% of the content. So this led obviously to the Nobel Prize, and this has been confirmed. This is a more modern Hubble diagram. Now the redshift is in log. That's why it looks linear. And when you do this now, the banana shapes of the energy components are smaller, and we're reaching 3% measure in the dark energy equation of states, W, 3. So this is many more supernovae, by the way. Before we had only 60, now it's more than 1,000. So now the question obviously is, now that we increase statistics, what is this dark energy really? Is it consistent with a cosmological constant? And it's interesting to see the latest results this year, last year. There starts to be a bit of a tension with the cosmological constant, which is a -1 for the equation of state. It's still below 3 sigma, but it's interesting. And you probably heard already, of course, about the Hubble tension. So the Hubble parameter is the expansion rate locally of the universe. And there are some discrepancies that I will briefly talk about. So we really need to understand a bit better our cosmology, and standardization of type 1a supernovae is key. In particular, this last Hubble diagram that I'm showing you here has another correction, a third correction, which is called the mass step correction. So I already mentioned there is this light curve width correction, there's the color correction. And if you do those two corrections and you do the Hubble residuals, so basically you subtract your apparent magnitude corrected by these two, you would expect everything lying at 0, right? But if you do those Hubble residuals as a function of the host mass of where the supernova occurred, you calculate the mass of that host galaxy, and you find that there is actually a step, sort of at roughly 10 to the 10 solar masses for a galaxy. You find a step, and okay, we don't know what it is, but if we apply this correction, our standard candles or standardizable type 1a candles are better. And that's how this last Hubble diagram was made, right? So at the end, then you have now three corrections: the stretch, Likert width, the color, and this mass step correction, which depends on the host mass. Obviously, this is a proxy for something that has to be related with the supernova, right? And this is one question that people are asking. And there are written claims that maybe it is due to dust extinction. This mass step correction has something to do with dust. But it's funny because the color correction, and I'm going to talk about it, maybe is also definitely related to extinction. So the problem with type 1a supernova is that people find these empirical relations and they try to correct them, but we have really never thought about the origin of these corrections. And maybe once we overcorrect with one, there appears another correction. So we have to be careful and we need to understand these corrections. And so, because I mentioned here extinction, let me just briefly recall what is extinction. If you're observing a source and you have some dust cloud, and you're observing on that side, right? The dust is going to preferentially absorb the light in the bluer wavelengths and scatter it in the bluer wavelengths. So what you're going to see is that you're going to see less light coming from your source, but also it's going to be reddened because you're going to obtain more red light. And this is why the reddening effect of dust as well. And this you can see obviously also here on Earth, the atmosphere has particles like dust, or you don't see here the atmosphere, but there's a layer here of atmosphere. And if you're at the sunset or sunrise, the light of the sun is going through a deeper layer, and it's going to scatter more the blue light, and you're going to see a redder effect in sunrise. And sunset is the same effect. So you can parameterize this extinction. There are two parameters. The A is the amount of extinction in the visible, in the V band. But the one that really tells you the shape of this extinction as a function of wavelength is what we call the RV. So here is the amount of extinction as a function of 1 over the wavelength. And so because these particles are small, they're going to absorb preferentially the bluer light. That's why you have more absorption here and less as you go to red, infrared, and so on. And so the typical value of the Milky Way is this 3.1 that you see here. It's an average of the Milky Way. Not everywhere in the Milky Way will have the same extinction value, but there are some others. But it's what we generally assume for other galaxies, for example. And if you have a lower RV, then you have a steeper curve, a steeper reddening curve. If you have a higher RV, it's going to be flatter. And what is this related to, this RV? Well, it's related to the dust particle sizes, especially. So if you have very small sizes of dust, then they're going to absorb preferentially the bluer wavelengths, right? So basically, you have a size distribution like this, and the value of the maximum, the peak of the distribution, you can see it here in the x-axis, and you can see the RV. So if your size distribution is smaller grains, then you have a smaller RV. If you have larger grains, then you have a bigger RV. Okay, so the RV, the dust extinction curve or reddening curve, parameterized with this RV, is related to the particle sizes. So going back to supernovae, I showed you this plot before. Each point is a supernova, brighter, bluer, fainter, redder. This is exactly the same effect than extinction, right? It absorbs more light and it makes it redder. So maybe this correction that we're making, it has something to do with extinction as well. Okay, but what if this beta, so if this is due to only extinction, this beta is related to the RV, to this parameter that of the dust extinction, right? But we know, and we are always assuming a single beta for all the type 1a supernovae, but they could be variations in RVs in different galaxies, in different lines of sights. And maybe this is something that is affecting our cosmology, right? So that's something to take into account, especially because people have found that there are differences in RV for different subpopulations of type 1a supernovae. Here's a color diagram. And there are two populations in red and blue. And the slope of this in this color diagram is related to the extinction curve, the RV. And you can see they have two different RVs, right? So maybe not all type 1As have the same extinction curve. And even if you assume they only have one extinction curve, and you calculate what that beta that you obtain from cosmology corresponds to for RV, you find a value that is very small, much smaller than the Milky Way value. And even if you study individual type 1A supernovae that have been well observed, and you can fit their light curves, assuming some intrinsic color for supernovae that don't have extinction. And the ones that have extinction, you can measure it. And some of them, you obtain RVs that are extremely small, right? Something much smaller than what we have seen in the Milky Way, lower than 2. Obviously, this is not all type 1A supernovae, but some of them. So all this long introduction to tell us the motivation for our project, which is to clean this dust, improve distance measurement for cosmology. But this also tells us about progenitors and galaxies dust. So this project is called CRISP, Correcting Reddening Intelligently for Supernova Probes. These are some of its members in Portugal, but also we have international collaborators, in particular here, Claudia and Luis. And so the questions I want to answer: what are the effects of these differences in dust extinction on the supernova cosmology? I already mentioned a bit of that. And what are the dust properties in different galaxies, right? And what are the effects on the supernova progenitors? So what are the effects on supernova cosmology? So I was mentioning that this beta parameter is related to this dust extinction, right? But I only mentioned that it has a component definitely coming from dust. But it turns out that type 1A supernovae, they're not all the same. Some of them are hotter, brighter. And it turns out that the ones that are hotter are also brighter. And the ones that are fainter are also have a less temperature, so they are also bluer. So there is two effects really in this color correction. There is the intrinsic color correction, and there is the dust extinction correction. And so we wanted to explore if this beta parameter really changes with the properties of the supernovae and of their host galaxies. And this is a work we did with Thomas de Jager. Here you can see the beta parameter, so as a function of the stellar mass of the host galaxy, and you can see that there is a change. So basically, we find that the beta parameter for higher mass galaxies is different. So this is related to the RV. So maybe there is an RV, different types of dust in different masses in different galaxies according to their mass. But also, if you look at you compare it to the color of the supernova, right? You see some differences. And remember, beta is related to RV through this RV plus 1. So this is the Milky Way value here. And you can see that as you go redder, basically supernova become redder. This probably means there's more extinction. And so what you're seeing is that it's approaching the value of the Milky Way. Whereas if you go to very blue colors, then maybe we're approaching the beta that is intrinsic. So basically this relation between temperature and brightness, right? So maybe this is proven differences in intrinsic and extrinsic effects. And this thing that finding different RVs according to the mass has also been found by other people. This is here the Hubble residuals as a function of color again for two populations according to different mass bins. And so you can see here these are massive galaxies, supernova in massive galaxies. These are supernova in lower mass galaxies. And they're going to apply different RVs as well as we find. They also find differences in RV for these two populations. And they claim that the mass step, remember this third correction that I talked about for type 1A supernovae, could be resolved by doing this, right? So basically applying two different RVs to two different population of masses, we get rid of the third correction of type 1A supernovae. Great, we have understood one. That's why they claim. We, on the other hand, this is a mass step doing different fits with different amounts of betas, so different RVs. We don't find that the mass step goes away. So we find that it affects it, but it doesn't completely go away. So we claim that the mass step, the third correction, has a dot component, yes, but it also has something intrinsic to the type 1a supernova. And so let me make a parenthesis because we're talking about cosmology to mention briefly the Hubble tension. So the Hubble tension is the measurement of the Hubble constant, right? And you can see here two measurements. So one is the nearby measurements from the Cepheids and type 1a supernovae, so the local distance ladder, we call it. And that one gives this blue. And as you can see, as a function of time, our measurements get more precise and the error bars get smaller. And then there starts to be a tension between those measurements and the ones of the cosmic microwave background, which is the red one, which is the one from the early universe, right? So at very high redshift, this is at very low redshift. And if you calculate this discrepancy nowadays, it's around 4, 5, even sometimes 6 sigma, depending on who you read. So let me just briefly mention the distance ladder, because that's the one that is related to type 1a supernovae. So basically what you have, because they're relative standard candles, you need to calibrate them, the type 1a supernovae. And what you do is you first use parallax to calibrate Cepheids in our own galaxy or in very nearby galaxies like the Magellanic Cloud. And then nearby galaxies where you have Cepheids, right? You then calibrate the ones that have Cepheids and type 1a supernova. You calibrate the supernova, and then you can go to the Hubble flow to measure the Hubble constant. And this is what's been done in these blue values here, and we find around 74 for the H naught, whereas the cosmic microwave finds 67 or something like that. Now, there's been studies showing there's a problem in this, maybe this calibration. So the galaxies that we use here, where they're Cepheids, they have, because they have Cepheids, they're star forming, they're face on, so that we can see the Cepheids. Whereas these ones that are higher up, there's a bit more mixed. And there's been some claims that if you standardize type 1a more carefully, according to this differences in property, this tension can be reduced from 5 to 3 sigma, right? And so let me show you the work that Gonzalo Martins has been doing. So basically, he takes subpopulations of the shoes sample and makes sure that the different properties are matched between each other. And so each point here is a subsample of matched properties. And he divides it into high stretch and low stretch. So high stretch meaning the ones that evolve more slowly of type 1a supernovae, and the green ones are the ones that evolve faster. So low stretch, right? And you can see that all of the ones, the subsamples that you do with low stretch have a significantly different Hubble constant. So basically just separating into 2 stretch bins, your shoe sample, you find an H naught in this case of 75, almost 76, compared to 71, 72. So there's a 3.5 sigma discrepancy between 2 subpopulations of type 1a supernovae. So this is huge, and that's why we strongly believe that the quoted shoes uncertainties and systematic uncertainties for type 1a supernova are underestimated. Why? Because type 1a supernovae probably have various subpopulations, and we're still using them as a single population to do cosmology, and this can lead to errors, but we should be more careful with our systematic uncertainty. Okay. So, I've been talking about dust, and dust is everywhere in the galaxy, so why not study the galaxies to see how is the dust, right? This is the work by João Duarte, a PhD student, and he analyzed here the dark energy survey galaxies by fitting stellar populations to the photometry. And here is the RV that he finds, and here's the tau v, which is very similar to the AV. So this is the amount of extinction. This is the reddening curve, right? Each point is a galaxy, and he finds this kind of relation, which seems weird. So the RV seems to be increasing as the AV also increases, right? And this happens both for global photometry or local photometry around the supernova position. And this goes a bit against what has been seen in some type 1a supernovae directly from the supernova light. And so what he says is, maybe this is an observational effect, and we have to remember that extinction is actually not the same as attenuation. So we talk about extinction when you have a point source. A supernova, for example, is a point source. It goes through dust, and it's only that light that goes through that dust. But if you're doing stellar population or galaxy studies, in reality, you have a bunch of different stars and a bunch of stars at different layers of the dust. So it's not more extinction, but we call it attenuation. And this can lead to interesting effects. For example, let's say you're observing at it face on, right? So you're gonna not face on, you're not gonna have as much extinction in general. But what can happen is that this light that goes towards the side, right, is gonna be scattered, but it's gonna be preferentially scattered the red ones because the blue ones, they might end up being absorbed, right, much more efficiently than the red light. Whereas if you're looking at it edge on, then you're going to have in general more extinction, but the stars that are on the edge are going to basically contribute to both the red and blue light. And so Joao says this is a reason for this, and not only Joao, but other people have demonstrated before. And to go beyond this, just a sketch and qualitative, he also did some simulations with radiative transfer simulation with SCIRT. This is a code where you can input source or distribution of sources, and you can follow the photons to see how they interact with dust. You can create the dust that you want, the dust composition, the dust sizes that you want. And so basically generating a fixed dust composition. So basically the RV should not change. And this is an aperture, so you can simulate with this SCIRT your instrument. And so he simulates here an aperture of 180, right? This is a very idealistic aperture. And in color here, you have the observing angle that you're looking at it here. So this is edge on, this is face on, right? And so what you can see, okay, edge on, I'm going to have more extinction. The AV is higher. My RV doesn't change. It shouldn't change because my dust properties are not changing. RV is really related only to grain size, right? So RV is constant, doesn't matter. But what happens when I take a larger aperture? This is 20,000 parsec aperture. I'm still simulating only one type of dust, but the RV I recover is going to be different. Why? Because of this effect. And you can see it here. So I was saying face on, right? You're going to have a much steeper, like the reddening curve, right? Much steeper means a low RV. So face on is here, and edge on, much more AV, but my RV is going to be smaller, higher, sorry. So this seems to confirm what we were saying qualitatively, and in fact also comparing with real data. Here you have in blue the simulations with SCIRT, assuming different types of galaxies and different amount of dust, but only one dust type. So the same grains, but just putting more or less dust. And these are the observations in orange, so we can find that trend, we can recover it. So basically, this is just an observational effect of scattering, right? And so you have to be careful when you're going to use RVs or extinction parameters from stellar populations to infer something about the supernovae, right? Also, in this, these are again the dark energy galaxies, the galaxies, and here's the AV, the amount of extinction as a function of the mass. And the blue points are the star-forming galaxies or younger galaxies, and you can see that as you have more mass, there is more dust. This is known. Whereas the passive galaxies, the ones that are not actively forming, as the red points here, they don't have a lot of dust. This has been known. And also for this is very similar to the RV, so the dust reddening curve. And you find that there's a difference between the young galaxies and the old galaxies. And this, we tried to simulate it with a single type of dust effect, just to see if it was an observational effect due to this dust geometry and scattering, but we could not reproduce it. So we think that this effect is real, that we have differences in RV according to the mass of the galaxy and according especially not only the mass, but also the age of the galaxy. So this effect might be real, and we're confirming what people have found with type 1 supernovae cosmology, but also with galaxy studies. So, okay, what I showed you, this was dark energy galaxies, it was entire galaxies, but what about if we go more local? And so this is, for example, one simulation of only one galaxy, again with skirt. So this is each point is only one region of the galaxy, 25 parsecs. So each one is one pixel. So basically, we're sort of imitating an IFU, an integral field spectroscopy observation. And what's interesting here is that you again find the same behavior, right? We're still modeling with one single dust distribution, right? So the RV, the intrinsic RV should be constant, but what we find is that there is this observational effect. And in color here is the distance from the center of the galaxy. So the ones that are when we are this is a Milky Way value here, and when you're very close to the center, right? So if it's a galaxy like this one, the bulge here, most of the light comes from the center, and so in the center there's not a lot of scattering because most of the light there is scattering but less, and so the scattering effects are here going to be lower. That's why you reach sort of the 3.1 value of the RV. But as you move further away, there is much more scattering. Light comes into here and goes into your line of sight. And so the effects of scattering as you move away from the center of the galaxy are going to be stronger. This also happens for the elliptical galaxy that we simulated. And so again, it seems that for local properties, even there, you also have to be careful with the dust parameters you obtain. And we also confirm this with real observations. This is a slab galaxy of a slab of a Muse galaxy. So each point is one of these pixels of Muse that we fitted, and we find kind of the same behavior. This is again RV versus AV. And so at the end, is this data useful for supernova or not? Well, it's complicated, but I'm going to show you here another study where they found again RV as a function of the distance, and you can see the RV goes down, so the same that we found with our simulation, right? So the RV at the center is more close to the 3.1, and as we move away, it goes away. And each point is a region of the galaxy. And these are regions around one supernova, but this supernova had a very strange RV, like I mentioned at the beginning, that some of them have very low RV. And this is really impossible to find with anything close, even taking into account scattering. So this approach is still statistically possible, and we're working with a large sample that we have with Muse, with Luis, of host galaxies of supernovae. So are there other methods that we can use to try to infer this RV, this dust reddening law? And I'm going to show you here what we're doing with polarimetry. So polarimetry of the light also tells us something important. So the light, the electric field, if it's randomly oriented, then we say there's no polarization. But if it has a preferential direction of orientation, then we say it's polarized, okay? And dust can polarize light through two mechanisms. One is dust scattering. So an unpolarized ray of light comes, interacts with molecule, for example, and if you're observing it at 90 degrees, then you're going to see a 100% polarization, right? Whereas if you see it just behind it, it's going to be still unpolarized, and in between, it's going to be partially polarized. This is due to dust scattering. But then in galaxies, dust grains, they can have, when they're non-spherical, they can be aligned through the magnetic fields of the galaxy. And if they align and unpolarized light comes in, the electric field in the direction of the alignment is going to be absorbed. And then we're going to see the perpendicular is going to come to us. It's going to be transmitted, right? And so we're going to see a polarization due to this alignment of the dust grains. And this dust grain alignment has this is polarization as a function of wavelength, has this particular shape. It's called a Cherkassky curve. And what's interesting is that the maximum of the Cherkassky curve, right, is related to the RV, the dust reddening value. So to the grain size, to the grain of the sizes of the grains for this relationship, right? So we can use that, and this is what João Silvestre, another João, popular name in Portugal, is doing here some fits of two different regions, Cherkassky fits. These are two good fits. These are bad fits. This is probably because there's scattering. So these are not taken into account, for example, this kind of fits. And when you do this and try to, you can map the whole galaxy, even when you have regions that you cannot adjust, you can sort of infer the whole spatial map. And then this is, for example, two different galaxies. This is the RV he obtains through the Sierkowski law of polarimetry as a function of the distance from the center of the galaxy. Each point is a region of the galaxy. This is the region of two supernovae that happen in this galaxy. And another galaxy, you can see that the average RV is very similar to the Milky Way, 3.3 in this case, 3.05, but there is a scatter. So that's interesting to keep in mind. And if you compare these are the values from the galaxy from polarimetry. If you compare it to the values from the supernovae, these supernovae that we observed are very low RVs. These are the values from the RV for different supernovae, and these are the values obtained from the galaxy. So you can see there's a clear discrepancy. So what is this telling us? Well, maybe the effects, maybe what we're observing with polarimetry is still a very large radius, and there's something very localized that is happening around the supernovae that dust properties are different, right? Maybe something from the progenitor, or maybe something even further out. And then let me show you another dust indicator you can use. So I showed you polarimetry, but you can also use spectra. And spectral lines like the interstellar medium. So there are ions like sodium, right? Like potassium, or like diffuse interstellar bands. And these create some absorption lines when the light of your star or whatever comes through the interstellar medium and is absorbed by this material. And it turns out that if you measure the equivalent width of these lines, they are good indicators of the dust. Here's the equivalent width and of sodium in this case. And here you have the EV minus V, which is color axis, so basically related to the AV, and you see a linear trend. You can do that also for, this is also sodium, but you can also do it for potassium, and you find this linear trend, right? So this is a work that, and there is a big advantage of this, using this equivalent width, is that the dust scattering in this case is negligible, right? Because it's not affecting the dust scattering affects the continuum, but not the lines. So Rita Santos is working on measuring the Muse lines and comparing them to supernovae. So here's a supernova galaxy, M100, which has hosted 7 supernovae, and this is the supernova spectra. So basically, from the supernova data, the supernova spectra, we obtain a very strong equivalent width, right? And using these relations that I showed you before, we can transform this equivalent width into an AV, so amount of extinction. Oh, I don't know if you see it, but this is the line. So this is AV, and this is the value from the supernova, right? But also you can measure the value from at the galaxy position, right, around the supernovae, and this is what you obtain, right? And also you can, with our skirt simulations from the Dustpedia simulations, we have very good simulations of this galaxy, right? And we can put the supernova at different depths in this diffuse interstellar medium. And these are this exercise, this point. So we're observing it from here, and then we go deeper into the position of the supernova, right? So we obtain this behavior here. So you can see that even if the supernova was at the other side of this galaxy, so the maximum AV we would expect is around 1, but we're measuring an AV of almost 3. So there is something either in our simulations or either, if our simulations are right, let's say, if that's all the AV there is, then there is something more localized, perhaps circumstellar material ejected from the progenitor, right, before the explosion, that is generating a higher AV. And in fact, this supernova is known to have very evolving lines of sodium. So they change with time, and this can only due to some material that is very nearby. So this way of investigating is a new way to find for example, if the AV of a supernova corresponds to the AV of the galaxy. And if not, maybe there's something else. So let me finish with, I already mentioned, what does this tell us about supernova progenitors? Well, I already just said it, but let me show you another piece of work. So if material is very nearby, then, as I was saying, the supernova light will interact with this material, and then you're going to see things changing with time, right? And so you would expect maybe RV or EV to change with time. And this is the work by Alejandro Yepes. So you can see here a supernova, particular supernova 2014J, and he analyzed throughout the light curve of the supernova what is the extinction parameter he gets. And this is EV minus V related to the AV, changes through time, but also the RV, you can see it changes through time. So maybe this material, at least for this supernova, there is something very nearby that makes it change through time. And in fact, you can compare this to radiative transfer models. This is from Bula, Mattia Bula. And so he puts dust clouds at different distances, 10 parsecs, 15 parsecs, 20 parsecs, 25 parsecs from the supernova. And these are the different lines, and these points are our data. And you can see basically that we can fix very well the data with around 15, 20 parsecs. So it's important to notice that this material is not that the RV changes, not because the grain's sizes changes, but it's again a scattering effect, right? So you have dust, this is the explosion, the light comes in, it reflects, and it goes into your line of sight, and you get maybe bluer light from before when the supernova was hotter, right? And this makes your RV change, right? So at least for this supernova, this is true, and this is the same that Katarina finds. If you model the distribution of colors, and the observed colors, you can measure it as an intrinsic component of the color, plus an extinction component and some noise, right? And you can subdivide your populations of type 1a supernovae, and some of these populations, this is their intrinsic colors, and here is the AV, and you can see that some of these stock populations have varying dust extinction. So it really seems that type 1a supernovae, at least a portion of them, a fraction of them, have some nearby material that makes it evolve with time, and maybe that's why we find these weird RVs, and that's why we also have to take that into account into our cosmology. And in fact, maybe this mass step that I mentioned before, the third correction, remember I said it's related to dust and it's related to intrinsic. Well, maybe the effect of the mass step is that it's a bit brighter in more massive galaxies, right? After the other corrections. So maybe you have light that interacts with the dust and come into your line of sight, and this generates a brighter. And it makes sense that it's in more massive galaxies where there's more dust, right? So the mass step could be related to dust scattering as well. So to summarize, so I think I showed you that dust extinction is super important. For cosmology, for type 1a, with type 1a supernovae, the calibration is extremely important. There is a color correction, but there's also this mass step correction, and they're both related to dust extinction, we think. And one of the key findings that people in the last 2 years are more and more convinced that type 1a supernovae are not a single population, but there are several subpopulations, and then we need to be careful once we are doing cosmology with them. Dust extinction in galaxies, well, I show you that you have to be careful with the difference between attenuation and extinction if you're using stellar population light, so from several sources. You need to take that into account and be careful with your conclusions, because you cannot infer directly an RV or dust grain size distribution from that. But we do find that it seems to be that there are two different reddening laws according to different galaxy mass and star formation or age. And then for supernova progenitors, there are peculiar reddening laws in some type of supernovae, and they do seem for some of them to be changing with time. So maybe there is some nearby material. It could be circumstellar material, but it could be also just interstellar medium that is nearby and that is very patchy. And so that's it. Thank you very much. And maybe you have questions.
All right, thank you. That was a very interesting talk. Dust is all. Are there any questions from the audience? Yes, please.
Hello, thank you for the talk. Very interesting talk. I have just two curiosities. Don't be afraid. The one that the work that you say about Rita Sanchez, I think.
Yes.
I mean, you say that she studied different supernovae in the same galaxy. I just think that the fact that the simulations or that the behind part didn't match with observation is because there are something around the there are several supernovae in that galaxy. So my question is, did you find the same behavior in all of them, or because this is, like you say, it's related with material?
Yeah, it's a very this is super new. Well, this plot. It was actually for an ESA proposal now. But what I can tell you is, okay, 3 or 4 of them we have spectra, and one of them has a very small AV. So it doesn't seem like like it would follow the same. That the other one, the supernova value lies within this range, and we haven't done the other ones. But this supernova, no, the other one was a core collapse.
Something that you remember is just, did you distinguish between the types or the?
This is the goal. I mean, the goal is to try to see differences between 1As and others. Yeah, but yeah, and this galaxy has many different types of supernovae, so that's good. It's a very good,
yeah.
very good exercise. Yeah.
I have.
Yeah, go ahead.
I think when one of the students in the following that one, how do you estimate the
Yeah, this is a very good question. Yeah, so if you're gonna infer color AVs, you need to know the intrinsic color, right? And if you have the intrinsic color in one band, you have the AV, and then the intrinsic color in different bands, you calculate the excesses in different bands, and then you can get the RV. So for the RV, you need color excesses in different bands, right? So it's super important, the intrinsic color template that you're going to use. That is the most important because it's going to affect your results for sure. So in this case, what we're using is the, Snoopy. So it's the Chris Burns fitter, and he has an intrinsic color law that sort of depends a bit on the stretch. It goes like this. So once you have the stretch, so the Likert width of the supernova, you compare with the template of the color template of that stretch, and you correct.
We use that only in that color, in that 2 bands. I mean, I have done that.
No. So we use many bands. I don't know how many bands this supernova has, but it also has, I think, infrared. This is very well observed. It has infrared, it has everything, and that makes your RV much stronger when you have the infrared because it serves as an anchor, right? And so the way we do it, if you want more, the way we do it, the evolution is to fit it with Snoopy only during certain epoch ranges, right? So from the whole, we get the other parameters like the time of maximum and things like that, and then we fix those, and then we let only RV and AV vary with Snoopy throughout the epoch ranges. That's how it works.
That is also, maybe you didn't say, but it is also good for the progenitor because if you have variation in dust, this means, like you say, that it has been expulsion of dust.
Yeah.
And that can also point you to one of the Taiwanese scenario for progenitor.
Yeah, absolutely.
If you have to white dust with, they are not extinction, they are not dust probably, but in the other one.
Yeah, so I didn't mention that in fact, but you're right. So we're thinking that there are more than one progenitor to type 1a supernovae, and if there is one population that always varies with RV and that has very nearby material, then maybe that would point towards a single degenerate. So remember the 2 scenarios that I mentioned. If you have 2 white dwarfs, they're very clean, the environment. Whereas if you have a white dwarf and a companion that is expelling mass, then it's more probable that there is CSM for that single degenerate scenario, right? Yeah.
Congratulations for the work.
Are there any other questions? Yes, please.
Hi, Santiago with the nice one. Type of
The muse with
music and galaxies.
Galax.
Yeah, this one. The other previous one. Yeah. Okay. So
These.
yeah, this is just curiosity. So you said that you assume that depending on the specs, at least for 518, blah blah blah. So I was wondering, you are trying to get acidic populations. You are inferring the priors when trying to fit out.
Yeah, because these are fits on the host galaxy populations, not on the supernovae. So yeah, we always take the same priors for all supernovae.
So these are global measurements for all galaxies.
These are localized. So this is a paxel of a new galaxy or Voronoi beam. Reality. Yeah.
Okay. Yeah.
Thank you very much for the talk. I have a question about when you showed the experimentation of using low stretch and high stretch.
Yes.
So my question here is, when you make that plot, is it only using normal 1A, so no 91B, so 91C?
This is the shoe sample. So it's exactly the shoe sample, the meaning, yeah, there are no peculiar supernovae.
Okay, I saw over here. Yes.
Super interesting talk, thank you. My question relates to your code that you used, the dust code skirt, right?
Skirt, yes. Not my code, by the way. It's from Martin Baas and the Belgian group. Very powerful, very powerful. I recommend it. I love it.
That seemed very interesting.
Yeah.
To differentiate attenuation and extinction. So I'm just wondering if you were to include in the galaxy simulation or the model you run the radiative transfer on, if you were to include a local density variation, would that affect the RED evolution you see?
Course,
because the ISM is in reality super clustered at very small scales. Like we see that a lot, and I think local density variation could explain also some part of it. Or
totally, yeah. So yeah, you're absolutely right. So the way we're doing the simulation, so for this part of when I was talking about Joao, it's very smooth distributions, both of stars and dust, right? So we know that they follow an exponential profile, right, as a function both of disk but also height, and that's what we do. So it's simplistic simulations in this case. And in these ones that I showed here also at the end, they're the same simulations. Yeah, so here we're putting supernova at different depths, but these distributions of dust are very diffuse, very continuous, let's say. And so the fact that we find here a much higher AV value, yes, it can be the circumstellar material, but it can be due to non-homogeneities, right? So the total dust is very well sampled for these Dustpedia galaxies because they've done these simulations. We didn't do those, including a lot of images from radio up to, so the dust mass, I think, is very well constrained. So I think this is true as a total, but you could have, but it doesn't have to be diffuse, and that's what we're assuming, yeah, that it's very diffuse. So these are either telling you it's very inhomogeneous or it was emitted by the progenitor, right? So that's why I think I say, yeah, patchy ISM or CSM. It's not necessarily CSM. It could be that it's very inhomogeneous. And now going back to the question, yeah, you in skirt you can. It's very versatile, so you can input inhomogeneities.
You can put in anything you want.
Anything you want. You want. Yeah, very powerful.
so if you see the scattering effects be different as a function of the inclination of the galaxy, whether or not you include homogeneity.
Yeah, we haven't done that, but what we did, and we discussed it in this paper, I recommended, Duarte is this year, Duarte 25. What we did do, because at first we were using very simplistic, for example, SCDs of stars, and then we started playing, I think we had one population for the bulge, one population for the disk. But if you start doing different distributions of stars, the scattering is going to also change, your effects are going to be different as well. So it's a very tricky thing, this scattering. And I think, I mean, I'm not coming from the galaxy community, but I've talked to some of them recently, and this is not something that is being very taken care of, I think. So sometimes you see 40% of the light that is coming to you is from scattering. And when we do typical fits, it's we assume that the stellar population is the only thing that comes to us, but there is a lot of scattering coming, and I think that might affect everything we measure.
Okay, I have one final question myself. So you leave us a little bit hanging at the end. So do you think that, because this seems to be the main question or the main motivation of your research, is closing or lifting the Hubble tension, no? Do you think the Hubble tension could be lifted by something as mundane as dust? No,
So
I mean, it's really very promising what you're doing here. What are the prospects, you think?
If the only measurement from the local universe was step-phase and type 1a supernovae, I would tell you definitely. I don't trust the systematic errors of type 1a supernovae. I think we are not measuring it properly and we need to improve.
Yeah.
But having said that, there are other probes completely independent of type 1a supernovae that are also finding high values of the H0. So perhaps the tension is not as large, but I think there's still a tension. Even when we do it, like you see this result here, we get 71, 72. So it lowers the tension, but it doesn't disappear. So I think there is a bit of a tension, definitely. Right. But I also think we have to get better type 1As. At least from my community point of view, we can do much better. Than
the result about those different populations was very illustrating in that sense, I guess.
I don't know where. Here.
Yeah, that one. Yeah.
So you see this one is 70, 72 almost. So it's still not. It's still a two free sigma for sure. Yeah.
All right. Okay. I think we should leave it here because pizza is waiting for us. So let's thank the speaker again. And pizza should be ready downstairs, but please wait with eating until